Hello everyone, welcome to this eighth tutorial session in the subject structural dynamics. Today we'll be studying about time history analysis and the response spectrum analysis with respect to multi-degree of freedom system. So let's start. Uh, Here I would like to point out that last week a few questions were raised that something was the answers given in the assignments were wrong. So I tried to contact the NPTEL team, and they told me uh, the NPTEL team told me if there is any error in the assignment, like the students can raise concern in the discussion forum, and it will be taken up. And one more thing is one question, one regarding assignment 6, there was a confusion. So regarding one question, so we can quickly discuss that. And the recording for the seventh tutorial session, it will be uploaded soon. I will have to re-record it and upload it because somehow it got corrupted. So I'll do that as well. So hang on for a second. I'll pull out the question. So, okay, this was the question where it was mentioned that this is a single degree of freedom system. It's a water tank. The height is 25 meter, and self weight of the tank is given as 45,000 kg, and the stiffness is equal to 700 kilonewton per meter. And it has been given that the damping is 5%, and the water tank is to be designed for the El Centro ground motion characterized by this response spectrum as shown in this figure. And we had to calculate the maximum deformation of this single degree of freedom system. So since the mass and stiffness has been given, you can calculate the time period of the structure. So once you can read the time period of the structure, and here note that it is given that uh, the ground motion is characterized by a response spectrum where u ground double dot is zero point 0.5 g. So just keep this in mind. Now have a look at this response spectrum. We know that for very stiff system. So I'll get back to those notes so that it becomes easier. Um, just trying to find the notes where, okay, this was where, yeah, this was what I was trying to find. So we know that when the system is very flexible, then what will happen? That is when the time period is very high, then um, then the ground u ground maximum is equal to spectral displacement, and when it is very stiff, we had also looked at that case, when it is very stiff, then SA spectral acceleration is u ground max double dot, like basically the ground acceleration and the body's acceleration basically matches. So why did I show it now? I'll just explain. Here you can see my, I hope you can see the pointer. Here you can see that if I draw a line here, the time period is like very low. When the time period is very low, means it is a stiff system. And if you draw a line parallel to this very stiff system, this portion, you can see that it will touch this line of A by U ground double dot 1. And we know that like uh, this ratio should be 1 for very stiff system. That is the the PGA for this ground motion, the peak ground acceleration is 1. Also, if you draw a line here, you can see here, if you see this, for very flexible system, we know that the ground displacement and the displacement, the maximum displacement of the ground, that is the PGT, should match with the spectral displacement. And here also this ratio comes out to be 1. So like basically what I want to show this is this plot is for 1g, and here ground acceleration is 0.5 g. So basically whatever value you get from this plot, you will have to scale using that scale factor of 0.5 g. And see, if here the time period is around, I believe around 1.59 seconds or 1.6 second. So 1.6 second you go here approximately, and you want to find displacement, so you come here. So this comes out to be approximately, so around point around point 0.5, point 0.4 between this, and point 0.5 into the scaling factor 0.5 comes out to be 0.25. So the answer lies in this range. So this is how you can solve this question. So I hope this question is clear. So mm, any doubts in the seventh assignment, in the assignment we just got over? Okay. See, in the question, it is given that the U ground double dot. Basically, this means the maximum, the PGD. Like we had discussed terms like when you have the ground acceleration, you can integrate it to get the ground velocity and the ground displacement, and you can calculate the maximum values and can calculate terms like p ground uh, displacement, p ground velocity, and p ground acceleration. Like these were discussed long back. So here it is telling that the ground motion for which the structure has to be defined, that El Centro ground motion, is characterized by a response spectrum where this number U ground double dot is 0.5 g. And in this plot, we know that for very stiff system, the ratio of A by U ground double dot. I just showed you that for very stiff system, this ratio should be 1 if this plot has been scaled uh, for the maximum value for the peak ground acceleration. And we can see that here, if you extend this line, it will it will cut this axis at 1. This means that this plot is for U ground double dot 1g, but you want the value for 0.5g. So basically all the values will be scaled by 0.5g. So I hope this is clear. If not, we can again take it up uh, at the end. So let's start today's topic. And if you have any doubt in the seventh assignment, then you can write your doubts in the chat box. We can take up those questions as well. Now let's start. Uh, what is we ended with modal orthogonality, and I also quickly showed why modal orthogonality is important, how is it actually implemented. So today also we'll since it was formally introduced in the class, in the lectures, in this week's lecture, we'll look at the concept once again, and then we'll solve a question with where that concept is being used, right? So for explaining it, I'll basically take up a building. We'll start from calculating its mode shapes and uh, frequency, and then we'll finally use that to do use the modal orthogonal property, and we'll solve that multi-degree of freedom system. And then we'll let's see how we can extend that question. So this is tutorial 8. We'll be first looking at time history analysis. So we had already discussed that, like, suppose we have a two-story building, then we uh, assume that like the seismic masses are concentrated at the specific floor level, and we convert into that lumped mass kind of model, and we write the stiffness matrix, and we learned how to write the mass matrix, stiffness matrix, damping matrix. Like, what did we do? We drew the free body diagram of those masses, and we wrote down the equation of motion, and we combined them to write them the matrices. So till that point, it was done. I'll write that part so that, suppose this is mass M1, this is mass M2, this is mass M3. Here the stiffness is K3, damping is C3. This is K2, damping is C2. This is K1, damping is C1. The mass matrix was found to be M1 0 0 0 M2 0 0 0. The stiffness matrix was found to be K1 plus K2 minus K2 0 minus K2 plus K3 minus K3 0 minus K3 and K3, and damping matrix is C1 plus C2 minus C2 0 minus C2 plus C3 minus C3 0 minus C3. And we can write the equation of motion as m u double dot plus c u dot plus k u is equal to f of t. Right. Now for ground motion, we know that what is f of t? F of t is nothing but m u g double dot double dot. This is as a function of time, right? Why is this multiplied by 1? This you can understand. Since mass is basically this will be a vector. Let's say mass is a 3 by 3 matrix, and basically you have three equations. So this should be a vector of 3 cross 1. To make it a vector of 3 cross 1, your mass is a 3 cross 3 matrix. This UG count as a function of time is basically a function of time. So, and this one is a vector of 3 cross 1 is basically. So finally, on multiplying, this becomes a 3 plus 1 vector. This is what we want. That is why it is written in that format. Now, we had learned in the earlier class that we take u to be equal to phi times q, and then we see that phi is a function of the spatial quantity and q is a function of time. So u dot is equal to, no, there is no limitation on the stiffness that K1 is greater than K2 is greater than K3. There is no such restriction while writing the stiffness matrix. I hope I'm getting your question, but there is no such restriction on the stiffness matrix that K1 should be greater than K2 and that should be greater than K3. Phi is equal to Q dot and u double dot is equal to phi q double dot. Now substitute it in that equation, substitute this value in this equation. What will you get? M u double dot becomes phi q double dot plus c u dot becomes phi q dot plus k u becomes phi into q into minus m u g double dot with this unit vector. Now pre-multiply with phi transpose. Pre-multiply by phi transpose. So I pre-multiply with phi transpose. Phi transpose m phi q double dot plus phi transpose x phi transpose k phi times q is equal to minus phi transpose m g double dot. Now from modal orthogonality, we know that the phi transpose m phi transpose m phi will be a matrix which has only the principal diagonal elements. Basically, let me call it mn. So phi transpose, this will be mn q double dot. Phi transpose c phi cn q dot plus phi transpose k phi kn q is equal to minus phi m ug double dot 1. And what is this mn? This mn will consist of only principal diagonal entries. Let me call this m11, m22, m33. It will have only these entries and all the other terms will be 0. Similarly, what will be Cn? Cn will also have only principal diagonal entries. That is C11, C22, C33 and all the entries. All the off diagonal entries will be 0. And find similarly Kn will be K11, K22 and K33 and all these other terms will be 0, right? And this phi transpose M, this is basically, see, phi transpose will phi transpose M be? It will be, here the mass matrix is made up of M1, M2, M3. Basically this M1, M2, M3 terms will come into picture multiplied with certain quantities. Let me name as M1, M, M22, M33. That's multiplied by UG double dot. Once I do a question, this will be clear. I'll be going through all the steps in that question. So finally, we can see that here, uh, because of this introduction of this coordinate u is equal to phi q and then pre-multiplying, earlier what was seen, this equation of motion mu double dot cu dot plus ku is equal to f of t. This was a coupled equation, but now we can see that the equation has been decoupled. Why decoupled? You can see the off diagonal elements are 0. So uh, if you see this so let's say kn term, k11 will be multiplied with q1 in the first equation. In the second equation, k22 will be multiplied with q2. And in the third equation, k33 multiplied will be q3. So that q1, we get separate equations for q1, q2 and q3 and thus they are becoming uncoupled. So If you write them, the uncoupled equations are M11 Q1 double dot plus C11 Q1 dot plus K11 Q1 is equal to minus 1 1 UG double. Similarly, M22 Q2 double dot plus C22 Q2 dot plus K22 Q2 is equal to minus M22 UG double dot. Now, suppose I divide by M throughout in the first equation. So, it will be the form Q1 double dot plus C11 by M11 Q1 dot plus K11 by M11 Q1 is equal to minus M11 UG double dot divided by M11. So, you can write this second term as C by M is 2 zeta omega, and we had learned this in the single degree of freedom class. So we can use this concept here also. 2 zeta 1 omega 1 q1 dot. Similarly, K by M is omega n square. We had learned this in the single degree of freedom system. Similarly, we can use it here. Q1 is equal to minus this term is known as the participation factor. So let's write this as P1 into UG double dot. This just tells us that how much uh, response, how much percent, like what part of the response is being contributed by this degree of freedom. Like this Q1 coordinate is related to the first mode. Q2 is related to second mode. So this P1, P2, P3 terms will just give an idea about how much to that response is being contributed to that by that particular mode. So we can see that okay, I should not have written Q11. This is Q1. Similarly, this is Q1. Right. So basically, for let's say ith mode, the equation is Qi double dot plus 2 zeta I omega I Qi dot omega I square Qi minus Pi Ug double dot. This is for ith mode. In the denominator, you have the term M11, which comes from this MN matrix. What is this MN matrix? Like if I want to write in the modal coordinates, this participation factor will be MN matrix, and in the numerator you have the phi transpose M matrix. And what is this Mn? This is phi transpose M. Mn matrix is phi transpose M phi. This is the, you can say this will give me the participation. If this is a 3 degree of freedom, it will give me the 3 participation factors. How did I get it? See, here, like I'm telling, this is the participation factor for this mode. What did I do? Here the denominator, I'm getting the term M11. Where does this M11 come from? M11 comes from this equation. from this equation. From where did I get this equation? From this equation. That is, by pre-multiplying by phi transpose, I came up with uh, the degree is, denominator is mass. No, denominator is not mass. The denominator is mn, which is basically phi transpose m phi. Mass matrix is with what I had started, which is m1, m2, m3, this mass matrix. But what I'm using here is mn, which is phi transpose m phi. Both are different. That is the denominator, phi transpose m phi. Okay. Yeah. This is what I missed one year in the numerator. Uh, when I'm when I'm writing it in matrix format, this one should also come into picture, right? Why one should come into picture? Because basically, if you think in terms of coordinate, what do I say? In matrix sizes, what is the size of the denominator? Let's say this is a 3 degree of freedom system. Mass is a 3 by 3 matrix. Okay, this you'll have to find for a particular. Um, no, it's better not to think in this terms. You can relate it like, what if I use, yeah, what if in this equation, what if I divide the equation throughout by phi transpose m phi? Then, as the participation factor on from the right hand side of the equation, if you divide this equation throughout by phi transpose m phi, the right side of the equation will be phi transpose m ug double dot 1 by phi transpose m phi. So the participation factor is, like, basically I am writing it in the form of some participation factor into ug double dot. So from there the participation factor comes out to be phi transpose m 1 by phi transpose m phi. I had missed this one factor. So now we have successfully decoupled the multi-degree of freedom system. Like earlier, this is a coupled equation. We cannot solve it, so we decoupled it and we got with this equation, which is a decoupled equation of motion. And now we know how to solve this. We know the techniques of solving single degree of freedom system, and we can use various we learned the new central difference method, Newmark beta method. We can use that method to solve this equation of motion, and then we'll have the results for various modes. You can simply add the result from various modes and get the total response. Once you get Q, you know that U is equal to phi into Q. Once Q has been identified, you multiply that with phi um, to get the U, right? So let's do an example so that this becomes clear. So let's start with a sorry. Let's see. We have a frame like this. Here the stiffness is 2K. Here the stiffness is K. Here the mass is M. Here the mass is 2M. Here the degree of freedom is U2. Here the degree of freedom is U1. And the height is H and H. First, we'll find the natural frequency and mode of the system. And this two-story frame is idealized as a shear frame. This means these beams are assumed to be actually rigid. The beams are assumed to be rigid. That is not actually rigid. I should tell E B is equal to infinity. So the first part of the question will be, this is a concept which we had already done in the last class. So let's pick it from there, and then we'll see, without calculating the modes, we'll not be able to uh, write U as a product of Q into phi. That is why I'm calculating phi first, and then we'll use this U is equal to phi into Q, this concept, and we'll decouple the equation, and we'll so equation of motion for the system, and then we'll solve it. Determine the natural frequencies and modes. This two-story frame is idealized as a shear building. And also I teach how do you mass normalize uh, mode shapes. I'll also show you that concept. So also it is given in the question that normalize the modes so that Mn is 1. And just now, what did we see? What is Mn? We want phi transpose M phi to be equal to 1. I'll show you how do we do this. Right. So first we'll write the mass matrix. So what will be the mass matrix? The mass matrix will be M1, M1 which is 2M, 0, 0, M2 which is N. Right. Then we'll write the stiffness matrix. Stiffness matrix is, the first element is K1 plus K2. That is, this is 3K. Then it is minus K2, so minus K, and K. This is how we write the stiffness matrix. There is no damping in the system, so no C matrix. And what is this K? Then let's uh, then we have to calculate the, what is that called, natural frequency. For that we'll write the frequency equation. Right, frequency equation is this determinant of k minus omega n square m is equal to 0. Right, so if we substitute it, calculate the determinant and all, I'm skipping that step here. since we had, I think so, we have done the same question or a question on the similar lines in the last tutorial as well. So, I'm basically skipping that step. So it becomes 2m square omega to the power 4 plus 5 km omega square plus 2k square is equal to 0. And the two roots are found. We find omega 1 square is k by 2m and omega 2 square is 2k by m. Now, once I get into the real concept, I'll stop skipping the steps. So from here, omega 1 is found to be k by 2m and omega 2 is found to be 2k by m. Right. Then we get omega 1 and omega 2. Then how do we find the modes? It is k by omega n square m multiplied by phi n is equal to 0. Substitute omega 1, get phi 1. You will get phi 1 to be half and 1. Then again use omega 2 in this equation, and then you will get phi 2 to be minus 1 and 1. Now I want you to check what is M1. M1 is, we just saw what is Mn. Mn is phi transpose M phi. I want to, so we saw Mn is, here when you use the complete M matrix, here phi is the complete modal matrix, but here I'm using this phi 1 transpose M phi 1. Basically, it is, I want you to calculate this. If you multiply this, you will get the number 3 by 2m. But I wanted this to be 1, phi transpose m phi to be 1. So what will we do? We will divide this each quantity by under root of 3 by 2m. Then what will happen? If I make phi 1, if I divide phi 1 by 1 by under root of 3 by 2m, half and half, what does the coordinates become? It will become 1 by 6 root m. So I'm multiplying by 2, and here this will become 2. Right? Now, if you perform this exercise, phi 1 transpose and phi 1, that is 1 by 6 root m, 1 into 2m 0 0 m, and 1 by 6 root m 1 and 2, you will find that this is equal to 1. So this is how you do mass normalization. This is quite often done to make the maths easier, so that is why I showed this step. So once this is done, then what do I want to do is by modal analysis, I want to determine the steady state response of the system, the second part of the question. So example, this was part 1. Now by using modal analysis, That is the concept which we just learned. Determine the steady state response of the system. Determine the steady state response of the system. So we just saw. Okay, let's consider in this question that the mode shapes are this which we just calculated. They are not mass normalized. This. So we just saw that omega 1 is under root of k by 2m, right? And omega 2 is under root of 2k by m. And phi 1 is half m1, phi 2 is minus 1 and 1. What is m1? M1 is phi 1 transpose m into phi 1, which is half 1 multiplied by 2m 0 0 m and half and 1. So this will come out to be half and 1. This will be m and m, right? So this comes out to be 3 by 2m. Similarly, do the same math for this m2, which will be phi 2 transpose m phi 2. Can someone tell me what will this be phi 2 transpose m phi 2? This will be minus 1 1, 2m 0 0 m and minus 1 1. If you solve this, you'll get 3m, right? And similarly, calculate k1. Why we are doing this? We had seen that in that coupled, when we are decoupling the equation of motion, these terms appeared. K1 is phi 1 transpose K phi 1. Again, what is phi 1 transpose? Half and 1. And what is K? We had written K matrix. This is 3K minus K minus KK. 3K minus K minus KK. And this multiplied by half, and what do we get here? Half and 1. Then we get 3 by 2k minus k, so k by 2. Then minus k by 2 plus k by plus k is k by 2. Then we get k by 4 plus k by 2. 3k by 4. Right. Similarly, calculate k2 as well. K2 is equal to phi 2 transpose k phi 2. And when you do the maths, you will get this number to be 6k. So this is some preparation which we did. Fine. Then we know that the decoupled equation of motion, how will it look? Mn Qn double dot plus Kn Qn is equal to did I specify? Okay, Yeah, in while doing the model analysis, I should specify to what force is the system subjected to. So here it is the same frame which what we dealt earlier. This was the frame, right? This mass was 2m, this mass was m, this stiffness was 2k, this stiffness was k, this is u2, it is u1, the beams were rigid, and this at this point you have a force of P naught sine of omega t. Instead of ground acceleration, in that example, in the earlier derivations, we saw ground acceleration term. Here I have a force of P naught sine of omega t. So on this side of the equation, basically I will have P n naught sine of omega t. And what is this? Uh, what will be P1 and P2? We just saw in the how did we calculate that decoupled equation? We multiplied this equation by phi transpose. So basically, on the right hand side you have the forcing function pre-multiplied by phi transpose. So you can write P1T. You'll just understand what is P1T. It will be phi 1 transpose into P of T. What is phi transpose? Half and 1. And on the degree of freedom 1, you have the force P naught. And on the second degree of freedom, you don't have a force, sine of omega t. Why you don't have a force? I'm referring to this. In the first degree of freedom, you have a force P naught sine of omega t. I'm referring to this point. And at that point, there is no force. Here, the force is 0. Let me write it like this. So if you solve this, uh, or maybe I should write it like this. This will be some phi transpose into some, okay, let me not mess up the notation. P n naught sine of omega t. It's basically the right hand side of the equation which we uh, studied here. This phi transpose into that original forcing function. So this comes out to be P naught by 2 sine of omega t. Similarly, you can calculate P2t, which is phi 2 transpose P of t, which is minus 1 P naught by P naught 0 sine of omega t. So this comes out to be minus P naught sine of omega t. Now, we'll use our knowledge of single degree of freedom system here. We know that the result of mu double dot plus ku is equal to P naught sine omega t. We know what should the solution be. Uh, when the governing equation is this, the steady state solution u of t is equal to P naught by k c sine of omega t, where c is equal to 1 by 1 minus omega by omega n whole square, right? Where omega n is under root of k by m. So this is from the knowledge of single degree of freedom systems. From that knowledge, we have this. So for a single degree of freedom, now draw similarities between this equation and this equation. In this equation, you have u double dot. In this equation, qn double dot. So if u of t is equal to this, then q of t is equal to p naught is the coefficient of sine of omega t. Here in this equation, the coefficient is Pn naught. So here this will be Pn naught by divided by k. Here you have k, here you have kn. So divided by kn, right? Then you will have, this is c, let's name it cn, and sine of omega t, same in both the equations, sine of omega t. So q of t will be of this format, or let's say this is not q of t, this is qn for the nth mode. For the nth mode, the equation will be something like this, where Cn will be 1 by omega n square, where omega n is the natural frequency of the nth mode. Now we know Pn naught and Kn for n is equal to 1 and 2. So let's take n is equal to 1. Then Q1t, it will be P10 by K1 C1 sine of omega t. Now P10, what is P10? This is P10, seventh, yes, seventh session as well as today's session will be uploaded. The recording of the seventh session, somehow it got corrupted, and I did not get time to re-record it. So over this weekend, I'll have to re-record that session, and I'll put up that session, the seventh session, and eighth session just after today's session. I'll upload it. So P10 is from here. We can see P10 is P naught by 2. P10 is P naught by 2. And what is K1? We had calculated K1 to be 3K by 4. Here, 3K by 4. 3K by 4. C1, let's write it as C1 into sine of omega t. So this comes out to be 2P naught by 3K C1 sine of omega t. Similarly, Q2T, that will be P2 naught by K2 C2 sine of omega t. P0 naught we calculate it, it is minus P naught. So minus P naught by K2, K2 is 6K, 6K C2 sine of omega t. So once you have Q1 and Q2, you can calculate U1 and U2. What will U1? We know that UN like the nth mode contribution to the displacement, UNT. UNT is the contribution of the nth mode to the displacement. Here N stands for the nth mode. It will be phi N QNT. So U1T comes out to be phi 1 into Q1T, and so phi 1, and I just calculated Q1T to be 2 P naught by 3K C1 sine of omega T. Then U2T, that is the contribution of the second mode to the displacement. It will be again phi 2 Q2T. It is phi 2 into Q2 is minus P naught by 6K C2 into sine of omega T. Now, total U will be contribution from the first mode plus contribution from the second mode, right? Or we can tell that, yeah, contribution from the first mode and the contribution from the second mode. So for the, or we can say for the jth floor, this is contribution to the jth floor from the first mode plus contribution to the jth floor from the second mode, where j is the, here j is number of floor. So let me substitute phi 1 and phi 2 and get u1 and u2. Let's get the complete expression. So we just wrote u1t is equal to phi 1. Phi 1 is half and 1 into q1t. q1t is 2 p naught by 3k c1 sine of omega t. So the contribution of the first mode to the first floor deformation is, we can write, like basically, let's open this. It will be P naught by 3K C1 sine omega t and 2 P naught by 3K C1 sine omega t. And contribution of the second mode will be minus half and half, and Q2T from here we'll use minus P naught by 6K C2 sine of omega t. So this comes out to be P naught by 6K C2 sine of omega t and minus P naught by 6K C2 sine of omega t. Done. Then what will be the total? I write it as just concerned because of my notation. And what I want to write on the first floor, U this is the contribution to the first floor from the contribution to the first floor from the first mode, and this is the contribution to the first floor motion from the second mode. So what is the total motion? Total will be P naught by 3k C1 sine of omega t plus P naught by 6k C2 sine of omega t. Similarly, for the second floor, this is, let me highlight it in a different quantity, different color. This is the contribution to the contribution by the first mode in the displacement of the second floor. So this is 2 P naught by 3k C1 sine of omega t minus P naught by 6k C2 sine of omega t. So minus C2 P naught. Yes, this is basically uh, the movement of the first floor, the deformation of the first floor, and the steady state deformation of the second floor. So once this is done, now uh, now here, so in short, what did we do? U n t is equal to phi n into q n t. So the contribution of, okay, basically this part of the question is done. Again, we'll be picking up next. So till here is this procedure clear. We decoupled the equation of motion, and then we solved it using modal orthogonality, and we came up with u1 and u2. C1 and C2 are not constants. C1 and C2 will come up from here. It is, if it is in terms of omega, right? The forcing function, and omega n is a known quantity. You already know what is omega 1 and omega 2 that I had solved in the first part of the problem. Yeah, this is omega 1. This is omega 1 and omega 2. If you substitute that, so they are basically functions of omega. So I've just made it concise and written it in this format. Okay, then so here you learned that the way you can calculate uh, deformations, that is u story deformations, in this way. You can also use this concept for any other response, and I'll show you what do I mean by this. So unt is equal to phi n qnt. We were writing this u is equal to phi into q. This is a matrix notation, and here I've written it in the form of equations. So this is the contribution by the nth node to u. It will come from qn and phi n, and combining you have to combine these modal contributions. So this un, like n, here n is the number of node. Basically you will have u1 coming from the first node, u2 coming from the second node, and if you sum up all these u's, you will get the total u, that is the nodal displacement. basically uh, nodal displacement u of t will be summation n is equal to capital small 1 to capital N u n t, and this is nothing but summation n is equal to 1 to capital phi n q n t, right? So um, you can use this procedure to determine forces in the elements also. Let that response be R of t. Like I'm drawing analogy between these two responses. Then R of t will be summation of uh, contribution to that response from the various modes R1, n is equal to 1, n is equal to 2. So you are summing it over all the nodes. Suppose here that like you can sum up over all the responses and you can calculate the total response. Like let's say force in beam or force in the column. You can also calculate using this concept. Also, here I would like to highlight that we had learned earlier that FNT, that is base shear, is nothing but stiffness into deformation UNT, right? Now, what is K? K is M into omega n square Kn, you can tell, and phi Un is phi n QNT. So, using this expression, QNT you can solve since you know the result of single degree of freedom system. So, you are solving the eigenvalue problem, so phi n is known. You know omega n square and you know mass. So you can calculate the base shear as well. So this is also quite often used. Uh, it's since base shear is an important quantity. So now we'll take up the third part of the problem where I will calculate the spring forces, basically the base, the story shears in the system, and I'll be using two concepts, like the concepts which we just discussed, this one, as well as using simple knowledge that the story shear is a product of the story stiffness and into the story drift. We'll be using this logic and we'll see that we get the same expressions. So let's move to the third part of the question. Let's consider the same frame. We have to determine the spring forces or the story shear in the system. Determine the story shear VJT in the system. Uh, and we'll be considering only the steady state response. So, if the system is something like this is the system which we have. This is floor 1, floor 2. Right. In this floor, what is the shear? Let me write it as V1N as a function of time. It will be the stiffness of this floor K1 into the motion here, which is U1 T. Like, what is shear? Basically, what is this lateral force? It will be the stiffness into the into the story drift or deformation. Since here the bottom is fixed and this part is moving, you have u1t. What is the story shear here? Story shear here means if you cut the body at that level, what is the force which you will get? That is u on the second floor due to nth mode n will be k2 stiffness into u2n as a function of time minus u1n, because u1 the drift, the relative motion. So you can write it like this. Now what is u? U is basically phi into q. So you can, instead of u1 n, you can write phi 1 n t into q n t. Similarly, here you can write K2 into UNT, U2N. You can write phi 2N minus phi 1N and multiplied by QNT, right? Now you can substitute, let's say, the K1, K2 terms. Let's do it for the first mode when n is equal to 1. We know that K1 is equal to 2K, right? K2 is equal to K. This is standard in the problem. Then we know phi 1 is equal to half and 1. Basically, so phi first mode on the first floor is half. Phi first mode on the second floor is 1. Did you get this from here and here? First subscript represents the node and first subscript denotes the mode number and second subscript denotes the floor number. So from here we can get contribution to the first floor from the first mode. Okay, I should have written it like this. Since we are following this notation that first is the floor number and second is the mode number. So V11 V11 as a function of time. V from here we know it will be K1 phi 11 plus Q1. So K1 is 2K, phi 11 is half, and Q1 we had calculated that Q1 is this 2 P naught by 3K C1 sine of omega t. 2 P naught by 3K C1 sine of omega t. So this comes out to be 2 by 3 K and K go away, P naught C1 sine of omega t. And V21 as a function of time. V21 will come out to be K2 phi 21 minus phi 11 Q1. So K2 phi 21 we just found it's 1. Phi 11 is half. K2 is K2 is K, that is stiffness of the second floor, which is K, and Q1 is 2 P naught by 3K C1 sine of omega t. So from here K and K go away, half and half go away, so this is P naught by 3 C1 sine of omega t. Similarly, you can calculate using this same expression, using this expression, we just now did it for n is equal to 1. We can, that is for the first mode. You can do it for the second mode, n is equal to 2. So when n is equal to 2, phi 1, 2, phi, how did I write this? Phi 2 is minus 1 and 1. So phi first I write the floor number. So phi 1, 2 is minus 1. Phi 2, 2 is 1. And if you solve V1, 2, you do repeat the same procedure. You will get these numbers. And V2, 2 minus P naught by 3 C2 sine of omega t. So what is the total shear on the first floor? V11 as a function of time, V11, that is V here on the first floor because of the first mode, plus V on the first floor due to the second mode. So V1 as a function of time will be V11t plus V12t. So what is V11? 2 P naught by 3 C1 sine of omega t minus V12 is P naught by 3 C2 sine of omega t. You can simplify this to write P naught by 3 2C1 plus C2 sine of omega t. Similarly, what is V2t? V2t is V on the second floor due to first mode plus V on the second floor due to the second mode. And if you plug in the numbers, you will get P naught by 3 C1 minus C2 sine of omega t. So this is how you can calculate the base shear. So now we'll quickly take a break of about 5 minutes, and then we'll look at an alternative approach of calculating base shear using this expression which I had highlighted. Using this expression, this is very straightforward, and then we'll quickly touch upon that on the response spectrum method um, as well, which is like basically you are just reading the response spectrum, and then here you could directly add the contribution from the various modes. There, since from the response spectrum you are getting the maximum quantities, so it's not necessary that both the maximum quantities happen simultaneously. So you can't add the maximum value from the first mode and the maximum value from the second mode directly. You use various methods like SRSS, basically square the individual terms and then add them and take the square root. So SRSS is basically squaring the terms and taking the square root, or there is CQC, which has not been covered. It is used only when if the modes of the system are very close to each other. So let's quickly take a break of 5 minutes, and then we'll resume the class. Okay, let's resume the class. So, someone has posted a question. What is the equation used to decouple the equation of motion for multi-degree of freedom system? I believe this is a question in the current assignment. So, uh, I think so. So, it would not be correct to discuss it, but uh, we just discussed what is modal orthogonality. It just means that you get uh, that is the modes are if you plot the modes you'll see that they are orthogonal to each other basis, meaning they form a basis system, or you can say the three vectors are independent. And when you pre-multiply and post-multiply the mass matrix, the stiffness matrix, and damping matrix with our modal matrix, you get a matrix which has only principal diagonal elements. And we just discussed in the class what equation is used to decouple a multi-degree of freedom system. How do you go from u system from an equation where the variable is u to a system where your variable is q? You simply replace u with q times phi, right? So first, let's look at the alternative method for this part 3, where we'll be using this expression fnt is m omega n square phi n q n t. So let's copy this. We're using this concept now. So from here we write f on the jth floor due to nth mode t is equal to m omega n square mj, mass of the jth floor, into phi on the jth floor due to nth mode qn as a function of time. If you directly use this formula, for example, if when n is equal to 1, m1 is equal to 2m, m2 is equal to m. Again, we just discussed what is phi 1 1, phi 2 1. What is the meaning of these terms? If you substitute them, phi 1 1 is half, phi 2 1 is 1, omega 1 square is k by 2m. You will see that f11 t, j is 1, n is 1, omega 1 square m1 phi 1 1 q1 t. And if you substitute them, you will get p naught by 3 c1 sine omega t. Then you can calculate phi to 1, that is shear on the second floor due to the first mode. You will get this to be p naught by 3 c1 sine omega t. Then you should calculate f1 to t and f2 to t. I'm skipping these two terms. And finally, the shear on the first floor due to the nth mode will be the force on the first floor due to the Basically, here you are getting the story shears, right? Um, so let's write them so that you can match your answers. 2p naught by 3. Simply plugging values in this equation blindly. If you plug in, you will get f11, f21, f12, and f22. Now, shear on the second floor. This is the diagram. Shear on the second floor, you have, suppose, in the first mode, the force acting on the structure is, this is F21 first mode, F11 first mode. Let's not cut it like this. This will lead to confusion. So if I draw these forces, no, 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 this is uh, not flexibility. That was flexibility. F12 is equal to F21. This is, I'll show you. These are basically the forces. I'm showing with this F, I'm showing the forces. So this F11 is all the force on the first floor due to the first mode. And let me draw the second mode just beside it. This is force on the second floor due to first mode. This is the force on the second floor due to the second mode, and force on the first floor due to the second mode. So if I want to calculate the story shear on the second floor due to the nth mode, it will be F2n. Basically, if you cut the story shear here, how much resisting force? Just imagine you're cutting the story shear, a story there. What are you left with? If I draw only the upper part, F21, here the story shear should be equal to F21. So, if I want to calculate the total shear on the second story due to all the modes, V2 will be F21 plus F22. Now, I want to calculate V1n as a function of t. It will be F1n plus F2n. Why? Suppose I remove this cut. Now I make a cut here and here. Let's say in the first mode. What are you left with? Suppose I make a cut in the first mode. This is the force and this is the force. The forces are F21 and F11. What is for equilibrium? How much force do we need here? It will be simply, I'm using statics, F21 and F11. This is from the first mode. And simply if you write the same thing in the for the second mode, how much force do you need here? F22 plus F12. So what is the total shear considering both the modes? summation of these two. So if I put here n is 1 and 2 and n is 1 and 2, so I get the same value from this expression also. So either you can use this direct technique or you can use this technique which I just discussed. This is also straightforward. This is basically the story shear into the story drift will give the story shear. Story shear is stiffness of that story into the drift. So this is what I wanted to discuss here. Then this is done. Then let's move on to quickly. Let's look at the response spectrum analysis as well. So in the response spectrum analysis, again, you start with the same thing. You can build the stiffness matrix, mass matrix, and the damping matrix. And you have the coupled equation of motion. You can decouple the equation of motion using U is equal to phi into Q. Then you can solve that equation. Now, basically, mm, till you have this equation, Qi double dot plus 2 zeta, sorry, 2 zeta I omega I Qi dot plus omega I square Qi is equal to minus the participation factor into Ug double dot. Now, what will be the maximum value of, suppose you have had an single degree of freedom system. Let's say U double dot, let's not use U double dot, let's use the notation D, the notation which I used here to draw similarity. No, I had used, okay, this. I actually don't want to use U because we'll be using U later. So what I wanted to do, show that when we had this equation of motion mu double dot plus cu double dot plus ku is equal to minus ug double dot, we had told that the maximum value that of this, the u from the response spectrum, we had learned how to develop the response spectrum. What do you do in a response spectrum? You vary the time period of the single degree of freedom and for a fixed value of damping, and you calculate the responses like this deformation, velocity, acceleration, and you come up with the, like for the current example, let's consider you have the spectral displacement versus time plot, and it is something like this. And why I'm telling this, for this you can calculate u maximum is the spectral displacement value. Let's say the time period of the system is this much. So from here you can read that, okay, this is the maximum spectral displacement. So for this, drawing similarity between these two, so maximum of QT will be the spectral displacement. Just the only difference is it will be multiplied with this participation factor Pi. Once you at Q, you know that U. Now forget this U. This U was only for drawing similarity. U is equal to phi into Q. So U max will be equal to Q max, which is participation factor into the spectral display deformation multiplied by phi. Now here you should comment. Here you should pay attention to the Uij max, where I is for a particular mode and J is for floor. So in this way, you can find out the maximum response using the response spectrum. Right, using the response spectrum, you get this value. Now, you have the maximum values for various, how do I put it, for the various modes, for the first mode, second mode. How will you combine them? How will you combine them? So there are various methods like SRSS, which is square root of sum of square. I forgot this full form when I was discussing this 5 minutes back. So square root of sum of square and the CQC method. So basically, if uh, from the first mode, suppose you get U, sorry, from the first mode, you get the response as U1J, from the second mode U2J, from the second mode U3J, J is at various floors. Will you combine them? In the SRSS method, you will take square of them, add them and take the square root. You will get Uj at various floors. So this is the SRSS method. And yeah, and you similar question was also discussed in the class. It was simply like coming up to doing the eigenvalue analysis, calculating the mode shape and frequency. Till there, it's the same. Then, since you know the time period from the given response spectrum, a response spectrum will be given. From the given response spectrum, you can pick up the spectral displacements. Once you get the spectral displacement, you can calculate the participation factor. You know what is participation factor in the denominator. We just saw that it is phi transpose m phi, and here it is phi transpose m multiplied with that unit vector. So once you get the participation factor, the spectral displacement, and you already have the mode shape, you can just multiply them to get Uij and then combine them in this fashion. So like I can't solve a full-fledged question now. So so the modal matrix, which was found in the question, which is in the tutorial. The modal matrix is something like 0.445, 0.802, and 1. And you have, this is basically the first mode, like, okay, I can explain the notation. Then basically you will have some entries here and some entries here. What does this entry denotes? It is phi. The top matrix denotes the mode number, bottom denotes the floor number. So this is mode number and this is floor number. So this is phi first mode, second floor, phi first mode, third floor. Similarly, this will be phi second mode, first floor, second mode, second floor, second mode, third floor. Phi third mode, first floor, third mode, second floor, third mode, third floor. This is how, what does each entry mean in the model matrix. And then doing the eigenvalue analysis is simple. And from the time periods, it was found T1n is around zero point 0.2 seconds. Tn2 was around 0.07. Tn3 is 0.05. This is in seconds. And from here, the spectral displacement was calculated from the plots. Now, how do we calculate the participation factor? Let me show one example. We know participation factor is phi transpose n multiplied by the unit matrix phi transpose m phi. So, participation factor for the first mode. So, this will be phi 1 transpose multiply mass matrix 1 phi 1 transpose m phi 1. So it is phi 1 transpose. This is phi 1, right? So phi 1 is basically 0.445, 0.802 and 1. Mass matrix and phi 1 transpose is 0.445, 0.8. Right. 0.445, 0.802 and 1. And the mass matrix, if you look at the question, you will see that the mass matrix is 2250, 0, 0, 0, 2250, 0, 0, 0, 2250. And on the numerator, you will again have, so if you see what is the dimension of this matrix, 3 cross 3 matrix, 3 cross 1 matrix, 1 cross 3 matrix. So basically you will get a number in the denominator, which makes sense. Participation factor is one number, means the size of the upper numerator is also 1 by 1. Let's check if it's 1 by 1 or not. Transpose of 1, this will be of the size 1 cross 3. Mass will be a 3 by 3 matrix, and this is a vector of 3 cross 1. We just discussed it. This is also 1 cross 1. And what are the elements here? Mass matrix is same as this, 2250, 2250, 2250. And let me remove this. This is 1, 1 and 1. And this is 0.445, 1 and 0.802. Right. Here, if you plug in the numbers, you'll get P1. So you'll find that P1 comes out to be around 1.2204. And from there, you can find out the participation from using this P1, SD1. You can use this formula. P1 into SD1 will give and multiply with the proper model coordinate. You will get the P1 means you'll get the participation of the first mode in the various floors. Then do it for the other modes as well. Use SRSS and you'll get the answer. So this is how you do the response vector method. So do you have any particular doubts regarding what I covered today, or any doubt in the seventh assignment? I'll try to record the seventh tutorial in this weekend. And assignment 8, I can't discuss the assignment 8 because the deadline is still not over. But let's see if assignment 8, the deadline is still not over, right? See, if you have any I declared this. Told this right in the beginning of today's class. I emailed the NPTEL team, so they told me that if you guys have any problem in particular assignment questions, you feel the answer is wrong, or if you feel some data is missing, please raise the points on the discussion forum so that they can take up the questions. So that
I
was
have already mailed him 2 days back, madam, regarding this question, but no one can respond to him.
Yeah, they will respond. I have asked them. I've particularly pointed out. So this is the particular doubt where students have questions. So they have advised me to convey it to you guys that to write down in the discussion forum so that Professor Sir will take up the questions. He'll have a look, and all the other TAs. Basically the team will look into it. So, if you have in the a doubt in this eighth question, in the eighth assignment, you told me which question? Sorry, fifth question, right?
Yes, because the fifth question solved answer is useful for sixth question. So 2 questions are lagged due to insufficient data.
Yeah. So please write this down in the discussion forum so that they can directly have a look into it. So um, that that will help you, I think so. Any other doubts? Okay. If there are no more doubts, I'll close the session. Any other doubts? Okay, okay. Thank you.